Hi everyone, welcome back to my channel Vision Tutorials Khan. In today's video, I will be discussing guys about the arithmetic progression series. In part 1 of arithmetic progression series, I will be covering the 5 important concepts about arithmetic progression series. That is, we will be studying about the definition of arithmetic progression series, the notation of arithmetic progression series. Second, we will be learning about the derivation or the proof for the n term of an arithmetic progression series. Third, we will be learning about the derivation or proof for the sum of the n series of arithmetic progression series. Fourth, we will be learning about the miscellaneous properties of arithmetic progression series. And fifth, I will be teaching you guys about couple of problems in order to have better understanding of arithmetic progression series, where we will be given a particular series in which we need to identify whether the series is in arithmetic progression or not. If it is in arithmetic progression, to find out the next terms of the same series. So let's begin. First, we will be starting with the definition of arithmetic progression series. The arithmetic progression series, before getting into the definition, we need to identify that in mathematics, there are certain patterns which we observe in our day-to-day life. Since if we consider an even number 2, 4, 6, 8, 10, there is a pattern in that number. If we consider an odd number 1, 3, 5, 7, 11, there is also a pattern in that series of number. So what is an arithmetic progression series? It is one among the number pattern where we have three major number pattern in mathematics. First one is arithmetic pattern, second is geometrical pattern, third one is Fibonacci series. First we will be dealing with about arithmetic progression series. What is arithmetic progression? Arithmetic progression is a series where the difference between the consecutive terms of the series is constant. So what is arithmetic progression series? We will be learning with a small example. Consider an example. Example 1. Consider a series 2, 4, 6, 8, 10 and so on. In this series, we can see there is a certain pattern between the two numbers. We use the term consecutive in the definition of arithmetic progression. What is consecutive? Consecutive term means the numbers coming one after the other without having gap between the numbers. That's why it is denoted as it is called as consecutive. So in this series, the consecutive number to 2 is 4, the consecutive number for 4 is 6, the consecutive number for 6 is 8, the consecutive number for 8 is 10. So as by definition of arithmetic progression series, the difference between two consecutive terms has to be constant. So 4 minus 2 is 2. In these two consecutive terms, we have 6 minus 4 is 2. These two consecutive terms, 8 minus 6 is equal to 2. In these two consecutive terms, 10 minus 8 is equal to 2. Therefore, in the entire series, we observe that there is a common difference, that is 2, that is being constant over the entire series, and thus we call this series as an arithmetic progression series. Let us consider example 2. Example 2. In example 2, we will take, for example, odd numbers 1, 3, 5, 7, 11, etc. As by definition, we will go as per the definition, where difference between the two consecutive terms, 3 minus 1 is 2. Here difference between consecutive terms, 5 minus 3 is 2. Difference between consecutive terms, 9 minus 5 is 2. Difference between consecutive terms, 7 minus 7 is 2. Here also the 2 remains constant throughout the series, and this is also an example for arithmetic progression series. Consider example 3. Minus 20, minus 10, 0, plus 10, etc. Here let us consider these two terms. As by definition, we will go difference between the two consecutive terms. Minus 10 minus of minus 20. Right? Minus 10 plus 20, which is equal to plus 10. Right? Consider these two consecutive terms. 0 minus minus of 10. We get 0 plus 10. Plus 10 is the difference between these two consecutive terms. Between these two consecutive terms, plus 10 minus 0 is equal to plus 10. Since the difference is d is remains constant throughout the series, this series is also an example for arithmetic progression series. Let us understand the notation for the arithmetic progression series. Let us understand notation for an AP series. Let us consider notation for arithmetic progression series. An arithmetic progression series is usually given as AP series is given as A1, A2, A3, A4 up to AN. Right? This is the arithmetic progression series. As the term indicates, the first term of an arithmetic progression series is denoted by T1. Term first, T1. This is T1, this is T2, T3, T4, this is Tn. The first term of an arithmetic progression series is denoted by A. That is term A. The second term of an arithmetic progression series is given as T2 is equal to A2 is equal to difference between, since this is an arithmetic progression series, the difference between the terms of the series is common. It should be common and it is denoted by D. So we have A plus D. This is D is difference. So common difference is denoted by D. Common difference of a series is denoted by small d. And we have nth term of an AP series is denoted by AN. Nth term of an arithmetic progression series is denoted by AN. We also have last term of an arithmetic progression series is denoted as L. Last term is usually denoted by L. We also have sum of an arithmetic progression series is denoted by the symbol as N. So these are the couple of notations which we use in arithmetic progression to solve the problems. So let us go to the concept number 2, where we will derive the expression for the nth term of arithmetic progression series, or we will prove AN is equal to A plus N minus 1 into D. Quickly we will go on to the concept 2. The concept 2 is derive the nth term of an AP series, or in general in board examination they can also ask as prove AN is equal to A plus N minus 1 times of P. Like this problems may come. So let us go on to the solution. Let us consider the AP series. Let us consider AP series A, A1, A2, A3, A4, etc. up to A to the N. So this is the arithmetic progression series, where the common difference here, common difference is D. So we will quickly move on to the first term. First term of the AP series is given as T1 as we learned in the notation sign of arithmetic progression, P1 is equal to A1. Here A1 is the first term, which is equal to A. Equation 1. Please make a note of all these steps. So if you can also pause the video and note down all the steps. The second term of the AP series is given as T2 is A2, right? Since by definition the difference between consecutive term is constant. Since A2 we obtain A1 plus D, A1 plus D A2, A2 plus D A3, A3 plus D A4. So A2 is A1 plus D. From equation 1, A1 is equal to A. Therefore, A2 is equal to A plus B. This is equation 2. Alright, this is second term. Third term of the AP series. The third term A3 is equal to A2 plus D. A2 plus D, right? From equation 2 we have A2 is equal to A plus D, right? A2 is equal to A plus D. Therefore A3 is equal to A plus D, keep it in bracket, that is A2. A2 is A plus D plus D we have. A3 is equal to A2 plus D. A2 is A plus D plus D we have now. So A3 becomes A plus 2D. This is equation 3. Let's note down all the steps and clearing it. So we have derived the first term, that is A1 is equal to A plus D, that is A, which is all. We can also write this one as A plus 1 minus 1 times of D, because here there is no D term. So here also 1 minus 1 is 0. 0 multiplied by D is 0. So we will get A. This is equation 1 which we have derived. We also derived A2 is equal to A plus D. It can also be written as A plus 2 minus 1 times of D. Equation 2, right? The coefficient of D is 1. 2 minus 1 is 1. Here also coefficient of D is 1. Coefficient of D is 1. Nothing changes. A3 is equal to A plus 2D. A plus 3 minus 1 times of D. Equation 3. Similarly, we can write A4. See, 3 minus 1, right? Here also 4 minus 1. 3. You can write as 4 minus 1 times of D. From equation 1, 2, 3 and 4, we can generalize the concept to the nth term. That is, we have an is equal to a. See, in every term what we have, the a remains constant, whereas here this term minus 1, 3 minus 1, 2 minus 1, 1 minus 1, 4 minus 1. Similarly, n minus 1 times of d. So hence proved an is equal to a plus n minus 1 times of d. This is the basic formula of arithmetic progression series. To solve all the problems in arithmetic progression series, this is one of the basic formula we need to remember. We need to know also how we arrive to this formula. And usually in problems, they ask the first term a and common difference d to calculate n term in arithmetic progression series. So we will quickly move on to the third concept, that is derivation, or prove the sum of the arithmetic progression series. Please note down these steps. Okay. Third, we will move on to derive the sum of the arithmetic progression series, or prove that Sn is equal to half times of A plus L. N 1 by 2 times of N into L, A plus L, to prove this. Let's move on to the solution. So begin with the statement. Let us consider the arithmetic progression series as A1, A2, A3, A4, up to An. Right? We know that first term of the arithmetic progression series is given as T1 is equal to A1 is equal to A. Right? The second term of the AP series is given as T2 is equal to A2 equal to A plus D. Right? Third term of the AP series T3, A3 is equal to A plus 2D, and it goes on. Right? We also have last term of an arithmetic progression is L. We will give as L. L is nothing but An. L is nothing but An. So we have second last term of an AP is L minus D. Second last term. L minus D plus D is L. So L is the last term. Last but one is L minus D. Third last term of an AP series is L minus 2D. So note down this thing and I am clearing it off. Right? So we have arithmetic series as around A, A plus 2D, A plus 3D, A plus 4D, L minus 4D, L minus 3D, L minus 2D, L minus D, L. Right? Like this is the arithmetic progression series. A plus D, we have A, plus D. A plus D is A plus D. A plus D plus D is A plus 2D. A plus 2D plus D is A plus 3D. A plus 3D plus D is A plus 4D. Similarly, L minus 4D plus D is L plus 3D. L minus 3D plus D is L minus 2D. L minus 2D plus D is L minus D. L minus D plus D is L. Therefore, sum of an AP series is given as Sn. Here Sn is equal to A plus D plus A plus 2D plus A plus 3D plus A plus 4D plus goes on to L minus 4D plus L minus 3D plus L minus 2D plus L minus D plus L given as equation 1. Here rearrange this LHS, this right hand side, left hand side. Rearrange right hand side terms and rewrite. We get similarly left hand side doesn't change. Sn is equal to last term comes first term goes last. Nothing changes, terms remain same, just we are reversing the direction. L plus L minus D plus L minus 2D plus L minus 3D plus L minus 4D plus goes on plus A plus 4D plus A minus plus 3D plus A plus 2D plus A plus D plus A, equation 2. Now add equation 1 and 2 Add equation 1 and 2. Adding equation 1 and 2. For left hand side we have Sn plus Sn, 2 times of Sn. So now we are going to add right hand side. Right hand side, consider this term A and L, right? A plus D and L minus D. Consider this term. Consider this term. Consider this term. Consider this term. Here, consider these two terms. These two terms. These two terms. We can consider, right? Here we have A plus L, right? No, A plus L. Here A plus D, L minus D, plus D minus D get cancelled. We have A plus L. Here we have 2D minus 2D get cancelled. We have A plus L. Plus 3D minus 3D get cancelled. We have A plus L. Plus 4D minus 4D get cancelled. We have A plus L. Similarly, here we have minus 4D plus 4D, A plus L. Minus 3D plus 3D, A plus L. Minus 2D plus 2D, A plus L. We have plus 2D minus 2D, A plus L. A plus L. Since we have n terms in the arithmetic progression series, A plus L repeats n terms, n times. So we can write as 2Sn is equal to n times of A plus L. Therefore, Sn is equal to n by 2 into A plus L. This is the expression for sum of an arithmetic progression series. So here this is one of the important formula to remember, where we need to find the sum of an arithmetic progression series given first term and last term. Given first term and last term, a number of terms in the arithmetic progression series, we can easily calculate the sum. On the other hand, if the sum is given, number of terms of an arithmetic progression is given, and last term is given, we can calculate first term. Similarly, we can also have n by 2 into A plus L is A plus n minus 1 times of D. Last term, here L is equal to A plus n minus 1 times of D. You remember, last term is basically given as L is equal to A plus n minus 1 times of D. Therefore, it is also given as n minus 2A plus n minus 1 times of D. Here, if given some of the digits of arithmetic progression series will be given in the problem. First term will be given, calculate last term. If first term is given, to calculate the difference, we can go for this formula. So you can choose any formula to calculate or to solve problems on arithmetic progression series. The fourth important concept, we will be moving on to the miscellaneous properties of arithmetic progression series. Okay, fourth one is the miscellaneous properties of an arithmetic progression series. This is very important thing to remember. There is a miscellaneous properties of arithmetic progression series. Derivation is very simple. We need to remember the flow of derivation. If they ask in board examination any types of this kind of derivation, you can go with the approach which I am going with, and you can easily derive or you can prove the given statement. And also remembering this thing, we can help in solving the problems in competitive exams. So first is about, we basically have AK plus A n minus k plus 1 is equal to AI plus A n minus I plus 1. Now, in exam they can ask us, prove this. Prove this statement. In exams, board exam, usually they can ask us, prove this statement. And also we can, with the help of this problem, we can solve competitive exam problems. Okay. To prove this, we have solution. Consider the arithmetic progression series. What is the series you consider? A plus D, A plus 3D, A plus 4D. Consider this series. This is an arithmetic progression because the difference between D, first term is A, and this is even arithmetic progression series. So this is T1, this is T2, this is T3, this is T4. Or we can also give as A1, this is A2, this is A3, this is A4. right? Okay. As the term indicates, we have n is equal to, how many terms we have? We have 4 terms. N is equal to 4. Let k is equal to 3 and I is equal to 2. Let k is equal to 3 and I is equal to 2. In this definition, k is kth term, I is ith term of the arithmetic progression series. So we have left hand side ak plus a n minus k plus 1, right? K is 3, write down 3, n is 4, 4 minus 3 plus 1. So we have a3 plus a4 minus 3 is plus 1 plus 1 plus 1, 2. We have a3 term is a plus 3d. a2 term is a plus b. So if we add, we get 2a plus 4d. This is LHS. Right. Coming on to RHS. RHS we have ai plus a n minus I plus 1. I is 2. I is 2 plus a. N is 4 minus 2 plus 1. We get a2 plus 4 minus 2 is 3, 3 plus 1 is 4. A4 minus 2 is 2, 2 plus 1 is 3, right? So we get A2 is given as A plus D. A3 is given as A plus 3D. So we adding, we get 2A plus 4D RHS. Since LHS is equal to RHS, right? 2A plus 4D, 2A plus 4D. This equation helps good. Therefore, we have AK plus AK A n minus k plus 1 is equal to A I plus A n minus I plus 1 holds good. This is one of the important miscellaneous properties of arithmetic progression series. Quickly we will move on to the second property. Just pause the video and note down the steps. It's very, very important. Now, second concepts we will be going on is an is equal to 1 by 2 times of a n plus 1 plus a n minus 1. In exams they can ask us prove this. Prove this statement. In order to prove this statement, let us consider the solution again. What is the solution? Let us consider the arithmetic progression series. What is arithmetic progression series we will consider? Moving on to the concept of the second property of miscellaneous property, that is second miscellaneous property. Miscellaneous property of an arithmetic progression series. The second arithmetic miscellaneous property, this is the fourth concept which we are studying, right? The fourth concept. And this second property is given as an is equal to an plus 1 plus an minus 1 divided by 2. In order to solve this, consider an arithmetic progression. We have to consider an arithmetic progression a plus d, a plus 2d, a plus 3d. Right. Here we have t1, this is t2, this is t3, this is t4, this is a1, a2, this is a3, and this is a4. Right. This is a4. We need to find, consider left hand side. An is equal to, let n is equal to 3. If n is equal to 3, we have an is equal to a3 is equal to a plus 2d. Therefore, a3 is equal to a plus 2d. Multiply 2 on both sides. Multiplying 2 on both sides, we get 2 times of a3 is equal to 2 times of a plus 2d. This is equation 1. We also have, consider RHS. We have a plus n plus 1 plus n minus 1. As n is equal to 3, we have a3 plus 1 plus a3 minus 1. a3 plus 1 is a4, a3 minus 1 is a2. a4 is basically given as a plus 3d and a plus 3d. a2 is basically given as a plus d. We write a plus d. This is equal to 2a plus 4d. 2 is common, a plus 2d, which is nothing but a4 plus a2. Equation 2. From equation 1 and equation 2, RHS of equation 1 and 2 is same. Thus, LHS are same. That is 2 times of a3 is equal to a4 plus a2. a3 is equal to a4 plus a2 divided by 2. In general, we have, if it is an, we have an plus 1 plus an minus 1 by 2. This is a derivation for the second miscellaneous property of arithmetic progression series. Now we will be solving couple of problems where our series will be given. We need to identify whether the series is in arithmetic progression, and in order if it is in arithmetic progression, we have to find the next terms of the arithmetic progression series. Okay. Quickly we move on to the third important concept, that is here. Problems to state whether the following terms are in arithmetic progression. Problem number 1. Given term 3, 3, 3. To find whether this series is in arithmetic progression, if it is in arithmetic progression, find out next 3 digits of the arithmetic progression. In this term, this is T1, this is T2, T3 and T4. Right. To be in arithmetic progression, it should be T2 minus T1. We have to find out 3 minus 3 is 0. T3 minus T2. 3 minus 3 is 0. T4 minus T3. 3 minus 3 is equal to 0. Difference is 0. Remains same throughout the arithmetic progression. Therefore, it is arithmetic progression. It is in arithmetic progression. Says that the difference, common difference between the consecutive terms of arithmetic of a series remains same. Therefore, the series is in arithmetic progression. The next digits T5 is equal to 1, 2, 3, 4. T5 is equal to 4 plus D. 3 plus 0 is equal to 3. T6 is equal to T5 plus D. 3 plus 0 is equal to 3. T7 is equal to T6 plus D. T6 is 3. 3 plus 0 is equal to 3. Therefore, next 3 digits are 3, 3, 3. This is one kind of problem. We will solve another problem in order to get better understanding. Better understanding. Consider the second series, whether the series is in arithmetic progression or not. We have to find it out. 3, 3 plus root 2, 3 plus 2 root 2, 3 plus 3 root 2, and so on. We need to find whether the series is in arithmetic progression. If it is in arithmetic progression, we need to find the next terms of the arithmetic progression series. Here this is T1, T2, T3, this is T4, right? T2 minus T1 is equal to 3 plus root 2 minus 3. We get 9, we get what? Root 2. Similarly, T3 minus T2 is equal to 3 is 3 plus 2 root 2 minus of 3 plus root 2. Now we get 3 plus 2 root 2 minus 3 minus root 2. 3 cancel, 2 root 2 minus root 2, we get root 2 only. Right. T4 minus T3, we get 3 plus 3 root 2 minus 3 plus 2 root 2. We get 3 minus 3 root 2, 3 root 2 minus 3 minus 2 root 2. 3 cancel, 3 root 2 minus 2 root 2 get 2 root 2. So D remains constant throughout the series, and the series given series in arithmetic progression. It is in arithmetic progression. We will find next 3 digits. So T5 is equal to T4 plus D. T4 is 3 plus 3 root 2 plus root 2. We get 3 plus 3 root 3. 3 root 2. T6 is equal to T5 plus D is equal to 3 plus 3 root 2 plus root 2 is equal to 3 plus 4 root 2. 3 root 2. Here it is 4 root 2. Here it is 5 root 2. Alright. Fourth term is 3 plus 3 root 2. Fifth term is 3 plus 4 root 2. Sixth term is 3 plus 5 root 2. Similarly, as this one we have T6 plus D is equal to 3 plus 5 root 2 plus root 2, which gives 3 plus 6 root 2. Similar kind of problems will be asked in examination where a series will be given and we need to identify whether the series is in arithmetic progression or not. So this is the end of the part 1 of arithmetic progression series. In the next video, I will be making the part 2 on arithmetic progression, where the problems we need to identify the difference between arithmetic progression, the sum of arithmetic progression, some competitive examination based exam problems will be solved in the next part 2 of the arithmetic progression series. Till then, please subscribe to my channel, like, subscribe and share.
Thank you. Try till you succeed. Please like, share and subscribe to my channel, The Vision Tutorials Fun.